Yes. Okay, then hi everyone to this new session on our seminar on topological quantum computing. This time our speaker is Ulrich Krähmer from the University in Dresden, speaking on towards a homological Kitaev model.
Yeah. Okay, thanks very much. So yes, as that slide says, this is my joint paper with Sebastian on this matter, and I think as a general rule, whenever you think something is brilliant and you like it, this is Sebastian's work. But obviously, since he organized the seminar, he asked me to give this talk, so I do my best to present this stuff. Good. So as we just discussed, I was told the first half an hour should be very elementary, and I was unsure what that means. But obviously, speed me up, slow me down as you wish. Now, I should say I'm fairly new to this whole Kitaev model topological quantum computation business. So I come from Hopf-algebras and homological algebra. But obviously, these feature prominently in that story. And kind of, to me, I would say the Kitaev model or the various variants of Kitaev models have a few things in common. One thing is there are some geometric input data, which is some two-dimensional manifold. Let's say here it's compact, it's closed, it's oriented. So the manifold will be called capital sigma. And then what happens is that you draw a graph, capital gamma, onto that manifold. And one demands that this graph now cuts that manifold into small pieces called cells or faces. And these pieces should be contractible. So the manifold gets cut up into small polygonal cells. And then there are some additional assumptions depending on the setup on this graph. And I want to be in a setting where that graph has exactly as many vertices as it has such faces. And I want to be in a situation where I've chosen a bijection between vertices and faces, which kind of chooses for every face some vertex in its boundary. So some people would call this a choice of cilia, and then they draw a small wiggly line from the vertex into the face to which it is associated. Kitaev himself talked about sites. So a site is such a pair of a vertex in the boundary of a face. Okay, and well, in the original setup that Kitaev considered, which people seem to call the toric code, sigma is a torus, and the graph gamma is simply a square lattice drawn onto this torus, as you see in this picture down here. So one of each of these cells, each of these sites is then just a square, and you choose one of its four corners, say the upper left corner, as the associated vertex. And then you have indeed this bijection between faces and vertices. Okay, so this is the kind of geometric input data you choose, and then there is algebraic input data. And this comes in various degrees of generality, but it could be in particular a Hopf algebra. You could choose a Hopf algebra, Turley A, and well, you take many copies of that one Hopf algebra and you attach one of these Hopf algebras to each of the edges of the graph gamma. And the physical interpretation will be that the vector space which underlies this Hopf algebra is kind of the state space of some quantum system. So you simply have copies of a quantum system attached to all the edges of this graph. So the total Hilbert space of the model will then be a tensor product of all these copies of the Hopf algebra A. So if my graph gamma has Turley L edges, I will have an L-fold tensor product of that Hopf algebra A. I call that straight H. That's my Hilbert space. Although in what Sebastian and I do, the Hilbert space structure doesn't matter. So what we do is pure algebra. But we have a big vector space like this. And well, in Kitaev's original toric code, that Hopf algebra is simply the group algebra of the group Z2. In other words, as a vector space, it's just a qubit. It's the two-dimensional vector space. So when looking at things backwards, I would say Kitaev had the idea to say that the standard qubit, the two-dimensional complex vector space, has a bit more structure than just being a vector space. Think of this as a Hopf algebra and then beautiful math sentence. Okay. And well, what do you then do with this Hopf-algebra structure? Well, you use this to model interactions between those different quantum systems that you mounted to the edge of our graph. So the idea is that there will be two types of interactions, and one is somehow communicated over the faces, and the other is communicated over the vertices of this graph. And the two interactions will use the product and the co-product of that Hopf-algebra. Now, in the original toric code, when the Hopf-algebra is just the group algebra of Z2, things boil down to a kind of more elementary quantum mechanical situation where you say that to every vertex of my graph, I have associated an operator on that big Hilbert space H, and also to every face, I've associated an operator that acts on this big Hilbert space. So in Kitaev's paper, these are called Aij and Bij. The Ij enumerate the vertices and the faces. And then you write down a Hamiltonian, which is simply the sum of all these operators, or minus the sum of all these operators. However, if you go beyond that simple setting of the group algebra of Z2, it will not be just a single operator. You will have an entire action of an algebra, namely that Hopf-algebra, and you have a co-action of that Hopf-algebra. I will recall what that means in a minute. And together, this gives you a Jeter-Greenfeld module structure on this Hilbert space H. And in fact, not just one. For each site, you get one Jeter-Greenfeld module structure over this Hopf-algebra A, and they all commute with each other. So in other words, you get an A to the tensor S Jeter-Greenfeld module structure on H, where S is the number of sites, i.e. the number of vertices equal the number of faces. And then this is kind of the setup in which you study this model. And what Kitaev then did is he said, well, if you then take the invariant subspace of H, in other words, the Jeter-Greenfeld morphisms, the Jeter-Greenfeld module morphisms from the trivial Jeter-Greenfeld module C to H, I will expand on that later. You get a vector space P, which will be called the protected space. And why is that so? Because this subspace of H contains states which are in some sense topologically protected, as Kitaev argues. And as I guess everyone knows, the idea is use these states to kind of run your quantum computer and use this topological protection to prevent errors from happening. And as I said, I myself, I'm not from quantum computation. I come from algebra, and sort of what I found most thrilling is this theorem that Kitaev kind of observed in his original paper. Namely, he realized that although you needed to draw this graph gamma onto this surface sigma to set up the model, at the end of the day, the dimension of this protected space does not depend on the graph you've chosen. It is purely a function of the genus of that surface, as one sees if one generalizes the model to other surfaces. And for a torus, you simply always get a four-dimensional space. So you can draw different graphs onto the same surface. The finer the graph, the more topologically protected this protected space will be. So at the end of the day, kind of the message from the point of view of quantum computation is take a very high genus surface, draw a very fine graph onto this, and then you will have a big quantum RAM, which is very protected. And well, Kitaev himself, as I said, started off with the torus and the group algebra of Z2. And then many people have started to generalize this, replacing this group algebra of Z2 by Hopf-algebras, the surface sigma by more general surfaces, the graphs maybe by more complicated graphs. But in any case, when Sebastian and I started this business, kind of everyone assumed that the Hopf-algebras one uses are semi-simple. I will recall what that means. And this featured into the proof of this theorem, or its generalization to the generalized Kitaev models. However, kind of our feeling was we should be able to do without that semi-simplicity assumption. I mean, the semi-simplicity really featured in the proofs, but the feeling was this was kind of an artifact of the proof chosen. So we wanted to prove an analog of this theorem when the Hopf algebras are non-semisimple. And that will be kind of the main goal of today. Good. Obviously, if there are questions, just interrupt me at any minute. I do not see the chat, so Sebastian, shout at me if someone writes something into the chat, and I need to know this. Good. So second part is kind of that elementary introduction to what I'm going to do. So I'll recall briefly what a Hopf algebra is, and I will then say what a Jeter-Greenfeld module is. If everyone knows that, well, then we could skip that part. But there might, of course, people who don't. And I initially expected that all this stuff would come up in other talks, but I think so far the word Hopf algebra has never really been used. It was always about the quantum double of a finite group or about fusion categories. So this is where we'll try to be slow and elementary. Good. So I think we all agree what an algebra is and know that. So an algebra just means a vector space coming with a bilinear multiplication map, which I write always as you see here as, well, A tensor B goes to A times B. And this should be associative. So algebra for me always means associative algebra. And this allows me to just write ABC for what I get when I first take the product of AB and then multiply by C, or do it the other way around. Good. And when I have an algebra, I can then talk about modules over this algebra. It could be right modules. So I have some kind of right associative action of the algebra A on some vector space H, where I multiply vectors with elements of the algebra. And note, I will try to use some consistent use of letters. So small ABC will always be elements from some algebra or some co-algebra. Small u, v, and w will always be elements in some vector space. So think states of a quantum system. And there will always be also be x, y, z's, and they are elements from other stuff like groups or so. So whenever I see an ABC, think operators. Whenever you see u, v, w, think state, if you are more physically inclined. Good. So there are right modules. Dually, I can talk about left modules, where the algebra acts from the left. And then, of course, I can also talk about bimodules. So a bimodule is a vector space which at the same time is a left and a right module of my algebra. And the two actions commute in the sense that they combine again to such an associative map from A tensor H tensor A to H, where I multiply from left and from the right. And in which order I carry out these operations doesn't matter. Now, it's not a big deal, but I will always assume my algebras are unital. So there's an element 1 in A, which multiplies everything to itself. And I also want my modules to be unitary, meaning this element 1 in the algebra acts as the identity map on all modules. Good. So I think this is pretty clear. Now, it's when the co-algebras come where things get a little bit more awkward. But let's first see an example. And the basic example, which has featured in Simon's talk some 3 or 4 weeks ago, is when you have a finite group G, and you take the group algebra. That is, you take the vector space of all functions A from G to the complex numbers, that you equip with the multiplication called convolution, which is given by this formula here. This is an associative product. The unit element in this algebra is the delta function supported in the unit element of the group. And those delta functions supported in the group elements, they form a vector space basis of this group algebra. In other words, I can write every function A uniquely in this form here. And when I take the convolution product of two delta functions supported in X and Y, I simply get the delta function supported in X times Y. So this is the product of the group elements X and Y. In other words, that group algebra is just a linearized version of the group. I could also say I simply take the group elements and I take formal linear combinations of group elements and multiply these by kind of linear expansion of the group structure. And if you then work out what a left module over this ring is, it's the same as what one traditionally calls a linear representation of the group. So each group element gets assigned a linear map on a vector space. And well, if you ask what is a right module of the group algebra, you will find it's also a linear representation, because the inversion of a group element, which maps x to the -1, gets extended to an algebra morphism from the group algebra to its opposite algebra. And therefore, if you give me, say, a right module, and I then define the multiplication with delta x from the left to be the multiplication with delta x inverse from the right, this turns this right module into a left module. But I could also do this vice versa and go from a left module to a right module. So in this way, the categories of left and right modules get identified. And they're both just the same thing as linear representation of groups. Good. So now we co everything. So we can also talk about co-algebras. Well, they are now vector spaces with a co-multiplication. So a map going from A to A tensor A. And here it's already a bit more awkward how to write down such maps. And I use this Sweeler type notation. I do not write a summation sign. So this does not mean this is an elementary tensor. This is pure notation for writing this map. And multiplications were meant to be associative. Co-multiplications are meant to be co-associative, which in this Sweeler notation means this. Now, if I take an element A, I first apply this co-multiplication. I get A lower 1, A lower 2, and then I apply the co-multiplication again to the second tensor component. I get this stuff here. I want to get the same thing as if I get when I've applied to the first tensor component. And this allows me to then just denote this entire 3 tensor by A1 tensor, A2 tensor, A3. And just as I had this notation A times B times C without bracketing in an associative algebra, I'm allowed to do this, and it will be clear what I mean if one thinks this through. And then completely analogously to algebras, I can talk about left comodules and right comodules and bi-comodules over these co-algebras. And these will be vector spaces H with a map from H to H tensor A, or to A tensor H, or to A tensor H tensor A. And I will again use such a Sweeler type notation to denote these. This time an index 0 will appear, so the 0 is always what stays within H, so to say. Yeah? So this map spits out elements in A, which are then these V lower 1 components, and the V lower 0 are the components in H. If I would have a left coaction, I would write V minus 1 tensor V0 here, and this will come a bit later. Good. So now finally, what's a Hopf algebra? Well, for this one first has to talk about bialgebras. Bialgebras are algebras which are also co-algebras, and the co-multiplication should be an algebra map. And a Hopf algebra is a bialgebra for which this canonical map, as they call it, is a bijection. So you go from A tensor A to A tensor A. You first apply the co-multiplication to the first tensor component. This lands in A tensor A, and then you use the multiplication to contract the second and the third to go back to A tensor A. And if this map is bijective, we say curly A is a Hopf algebra. Now, I did stress that I want all my algebras to be unital, and by complete duality, I also want all my co-algebras to be co-unital, which means there is a map epsilon from A down to C, the ground field, which satisfies axioms dual to that of a unit in an algebra, which in this Sweeler notation I can write like this. So if I take an element, I first apply the co-multiplication, and then I apply this co-unit to either of the two tensor components. I get back my element A. And if I'm in that situation, I actually can verify that the inverse of this map gamma always takes a specific form. It's again obtained by taking a co-product, and then there is a linear map S, which one calls the antipode, which you imply here, and then you multiply here. So alternatively, Hopf algebras can be defined as bialgebras with an antipode, a linear map S from A to A, satisfies certain assumptions. But this definition in terms of the canonical map is in some sense a bit nicer, because it generalizes to all sorts of technical settings where you don't have antipodes. So if you want to talk about topological groups, so if you talk about locally compact groups or locally compact quantum groups, there are no antipodes any longer, but you still have this gamma thing. And if you go to quantum groupoids or Hopf-algebroids, again, in general, there's no antipode, but still you have this map gamma, which is bijective.
I have a question.
Yes?
So you define the Hopf-algebra condition to be on gamma being bijective. So that may determine the antipode S.
Yes.
Because you said in your third bullet point you mentioned S is the antipode, but that is that given or that's determined from gamma?
No, this follows. So the theorem is if this map gamma is a bijection, then there exists a unique linear map S from A to A such that the inverse of gamma looks like this.
Oh, I see.
Okay. And then you will be able to show that this map S that is uniquely determined by this condition satisfies the properties that you will usually find in Hopf-algebra textbooks. I mean, you can see how you get S, right? You apply gamma inverse to A tensor 1, take B to be 1, apply gamma inverse to A tensor 1, then you get A1 tensor S of A2, and then you simply hit A1 with the co-unit, and then you get S of A. And it's this gamma inverse, this map which sends A to A lower 1 tensor S of A lower 2 that features in many homological constructions. So in some sense, I would say this is a more fundamental map than the antipode itself.
Okay, I mean for Hopf-algebras they're equivalent, right? One determines the
exactly.
other.
When you talk about Hopf-algebras over fields, it's equivalent that there exists an antipode and that this map gamma is bijective. But if you would go to, for example, Hopf C star algebras, then that's no longer the case. Or if you go to multiplier Hopf-algebras or to Hopf-algebroids. So there are various generalizations of Hopf-algebra theory where you don't have antipodes any longer, but you will always have the bijectivity of this map gamma. So somehow this is the more fundamental definition of what it means to be Hopf, I would say.
Okay, thank you.
Good. Okay, so these are Hopf-algebras. Now we had this example of a group algebra, and the group algebra is such a Hopf-algebra that co-multiplication looks very banal. So in terms of the basis given by the delta functions, it simply maps each delta x to delta x tensor itself. In other words, if you give me an arbitrary function A from the group G to C, the co-product, the co-multiplication of A will be given by this expression here. And the antipode now really just maps delta x to delta x inverse. So it's a linear extension of the inversion of a group element. And the inverse of this canonical map is therefore given by this formula. Okay, so group algebras are Hopf-algebras. Now, why do we care? What's so nice about an algebra being a Hopf-algebra? Well, it implies that the category of modules is a very nice category. It kind of wants to be a rigid monoidal category. So to be a bit more precise, if you give me any algebra A whatsoever, you can talk about the category of its left modules or right modules. Let's focus on right modules for now. And if you give me two modules, K and H, in general, you cannot form any meaningful tensor product between K and H. But of course, in many situations like representation of groups, representations of Lie algebras, etc., we want to have exactly this operation. And a bialgebra structure is precisely what you need to do this, because you can then form the tensor product of the vector spaces K and H. So this is now the tensor product over K. And you can turn this into a right module again in this way. So if you give me an elementary tensor V tensor W, How do you act with an algebra element A from the right on this? Well, you first apply this co-multiplication. Now you are in capital A tensor capital A, and with the first leg you act on V, with the second leg you act on W. And one verifies, yes, in this way, the category of right modules will become a monoidal category. The unit object in that monoidal category is the ground field K on which the bialgebra acts by the co-unit. And what is this antipode thing good for? What is special about the algebra being a Hopf algebra? Well, the antipode of any Hopf algebra is an algebra antimorphism. So it reverses the order of multiplication. That's an easy juggling around with the Hopf algebra axioms. And what this means is you can also introduce the dual of a module. So if H is a right module over an algebra, then the dual vector space H star is always a left module over this algebra. You can always define a left module structure on that dual. But if you have that antipode, you can use this to turn that left action again into a right one. And the action is simply by acting on the arguments. So F is a linear functional in H star. I define a new linear functional F acted on by A. Small a is an algebra element. And it's the linear functional which maps V, a state, an element in H, to the value of the original functional on V acted on by S of A. If I wouldn't have the S here, this would not define a right action, it would define the left action of A on the dual vector space. But using the antipode, I can turn that again into a right module. And if I restrict to finite dimensional vector spaces, this will be a right dual in the sense of monoidal category theory. So I will have a right rigid monoidal category. And if that antipode is bijective, then with the same kind of formula, just with S inverse, I can also define left duals. So the upshot is a Hopf algebra with bijective antipode will have a rigid monoidal category of finite dimensional right representations. To have actual duals, I think I skipped that bit, the module should be finite dimensional as a vector space. So the upshot is finite dimensional representations of Hopf algebras. That's precisely where you get rigid monoidal categories from. And there's a more formal theorem, Tanaka prime reconstruction, which says basically if you have a rigid monoidal category and you have a forgetful functor to finite dimensional vector spaces, well, some additional axioms, adjectives have to be thrown in. Then it's the co-modules over a Hopf algebra, which are finite dimensional. And yeah, but if the Hopf algebra is finite dimensional, then that's that. Good. Now, I mentioned the word semi-simple, and well, I also said that the basic example of a Hopf algebra is a finite group algebra, and here two things happen to representation. First of all, if I have a finite group and I work over a field of characteristic 0, then Maschke's theorem tells us that every representation is completely reducible. It's a direct sum of irreducible representations, or in more categorical terms, every module is a direct sum of simple modules. And that is paraphrased by saying that the category of modules is semi-simple. Okay, so this is one adjective that can be there or not. And there's another thing which kind of goes towards fusion categories. The Hopf algebra, which is the group algebra, is co-commutative, and that implies that the category of modules is a braided monoidal category. I have a flip operator, simply the tensor flip, which identifies K tensor H and H tensor K not just as vector spaces, but as objects in that category, as representations of the group G. And for a general Hopf algebra, you cannot do that. Now, if you have a general non-co-commutative Hopf algebra, and you take two of its right modules, K tensor H and H tensor K might not be isomorphic as right modules. However, there is a universal approximation of each monoidal category by a braided monoidal category. You can pass to the so-called Greenfeld center of that monoidal category. And what is an object in that category? I mean, it's a category, first of all. It's a braided monoidal category. And an object is a pair of an object C in the original monoidal category. So here, a representation of my Hopf algebra. and a natural transformation, which kind of identifies the functors given by tensoring from the right and tensoring from the left in C. And well, that natural transformation should be nicely compatible with the tensor product. Okay. Now note, of course, this generalizes the notion of the center of an algebra. In an algebra, there's the subset of those elements which commute with all others. So those elements C, such that A times C is equal to C times A for all A. Now in a monoidal category, A times tensor C is maybe isomorphic to C tensor A in a nice way, but it could be so in different ways, even for the same C. So the choice of that chi is additional information. And if we are in the category of right modules over such a Hopf algebra, well, then this Drinfeld center of that category consists precisely of those things that I called Jeter-Drinfeld modules. And you can express what this means to be in the center in a more algebraic way, maybe, because if you have something in the Drinfeld center of the right module category, you can then write down a right coaction of that Hopf algebra on that right module. So you can go now from A tensor C to C tensor A using that braiding chi lower A. So the Hopf algebra A is a module over itself by right multiplication, so it's an object in its module category. Simply apply that braiding to one tensor C, call that the map from C to C tensor A in that Sweetler type notation, and then you verify that the braiding condition implies that this is the right coaction. So an object in the Drinfeld center becomes also a right co-module. Yeah, it was a right module in the first place, it becomes a right co-module, and then you verify that this horrible compatibility condition is satisfied. Which basically says something about how first acting and then co-acting commutes with first co-acting and then acting. Furthermore, in that situation, you recover your braiding using this formula here. So you can now braid this C over any other thing by co-acting and acting with the algebra things onto that V. And any Jeter-Drinfeld module arises like this. So in other words, the Drinfeld center of the category of right modules over a Hopf algebra can be canonically identified with the Jeter-Drinfeld modules over that Hopf algebra. And well, going back to the original situation, I said this is kind of the aim of the game, that extended Hilbert space of the Kitaev model should have such a Jeter-Drinfeld module structure. Now again, in our example, how do these Jeter-Drinfeld modules look down to earth? Well, they featured in Simon's talk. Now there are representations of the group G, which as a vector space come with a direct sum decomposition labeled by the group elements. But these subspaces CX, they are not just sub-representations. If I now act with a group element, I kind of shift that label by the adjoint action of the group on itself. And that's what a Jeter-Drinfeld module over a group algebra is. Okay, now last but not least, when the Hopf algebra is finite dimensional, there is what's called the Drinfeld double or the quantum double of the Hopf algebra. So this is a bigger Hopf algebra. It contains a copy of A as a subalgebra, and then it contains a copy of A star as well. Now, first one should say if the Hopf algebra is finite dimensional, then the dual space A star also becomes a Hopf algebra. And a co-module over the original Hopf algebra is the same as a module over A star and vice versa, where left becomes right and right becomes left. So A star is a Hopf algebra. I can take the opposite algebra to kind of fix this left becomes right. And so the Drinfeld double is a Hopf algebra, which contains A star op and A as subalgebras. And this gives me an exact factorization of that algebra D of A. So the multiplication map from this vector space here is bijective. And well, the module over this Drinfeld double is a module over A, because A is a subalgebra here. It's also a module over A star op. So if we say right module, it's actually a left module over A star, hence it's a right comodule over A. So indeed, a module over dA is both a right module and a right comodule over A. And the compatibility that was this Jeter-Greenfeld condition is built into the commutation relations between A and A star within D of A. So if you have a finite dimensional Hopf algebra, the Jeter-Greenfeld modules can also be seen as the modules over some Hopf algebra, and that's this Greenfeld double. Cool. So last bit of the elementary part. Now you can revisit kind of the protected space that we had. I said the protected space was the Jeter-Greenfeld module morphisms from the trivial Jeter-Greenfeld module to H. So now in this finite dimensional situation, I said Jeter-Greenfeld modules are just modules over this Greenfeld double of curly C, by which I mean the tensor product of these copies of A, S many, where S is the number of sites. And then the protected space is simply all the elements in my big Hilbert space, where all the elements of the Greenfeld double of C act by the co-unit of that Greenfeld double. And this is how I would think of the protected space. And now comes the point why I got interested in this in the first place. Now, this here is what Hopf algebraists would call the zeroth Gerstner-Schack homology of the Hopf algebra curly C with coefficients in this Jeter-Greenfeld module H. Okay, so in algebra there are many cohomology and homology theories of algebraic structures, like Lie algebra cohomology, group cohomology, Hochschild cohomology, cyclic cohomology, and there's also the cohomology theory of Hopf algebras and its Gerstner-Schack cohomology. And the coefficients of that theory are precisely those Jeter-Greenfeld modules. And the zeroth Gerstner-Schack homology takes precisely this, the invariance. So, so by very definition, the protected space is the zeroth Gerstner-Schack homology. And if you deal with semi-simple Hopf algebras, that's all there is to say, because semi-simplicity implies that all the higher cohomology groups are all zero, hence not so interesting. But if we could extend the Kitaev model to non-semi-simple Hopf algebras, then you could also look at the derived functor, the full Gerstner-Schack cohomology of the Hopf algebra C with coefficients in this extended Hilbert space, and this would give you an invariant of non-semi-simple Hopf algebras. And suddenly you could kind of turn things upside down and say, no, we can use quantum computation to define interesting invariants of Hopf algebras, of non-semi-simple Hopf algebras. And that's why I really get excited about this story. And that's also why we want to go to non-semi-simple. Good. Okay, that's the end of the elementary part. Are there any questions about this stuff so far?
I assume it always takes a minute or so to unmute yourself. So if there's questions, feel very much free to ask them. If there's a question during the talk, write to the chat, I'll read it. I also wanted to briefly point out, you mentioned this gamma map and later on the braiding. And both of these maps are up to a convention more or less constructed the same way. We're talking here about the braiding for Jeter-Greenfeld module. So it's quite interesting that you have these structures, antipode for Hopf algebra, and braidings on the center, and they somehow are connected by a map which looks pretty much the same.
Good point. Good point.
Are you going to say what kind of conditions is required on the non-semisimple Hopf algebras?
Yes, maybe I just draw a picture. Yeah, this is kind of what's going on. Yeah, you have two things, and then you spit something out, and the other strand absorbs this. And well, in the case of the Jeter-Greenfeld braiding, you then simply flop this around, and that's. But they're both of the same type. Okay, sorry, I interrupt you, Shawn. So what were you asking?
Sorry, I was asking. Are you going to say what conditions are required on the non-semisimple Hopf algebras? For example,
yes.
Yeah.
Yes, I will. So basically, at the end of the day, there will be two theorems, hopefully, and there will be assumptions made for the whole story to work. Yes.
And have you considered weak Hopf algebras?
No, good point. Yeah, we were considering going more general, but yeah, the paper got already way too long and we had worked already for too long on this. So we thought, okay, in the first paper, we focus on one aspect of generalization, which I will start with in a minute. And but yeah, definitely at the end of the day, I want a much more general story to appear here, including weak Hopf algebras.
Okay, good.
Good. So
Before we continue, can I briefly ask? Weak Hopf algebras also means Hopf algebra, but in a weird category, right?
No. I mean, weak Hopf algebra would be a Hopf algebraic, but not a Hopf algebra.
I thought there's a paper on this long this long forgetful functor where you first take all this. Okay, but maybe this assumes semi-simplicity, that you have to take all the simples and you forget to representations of a Frobenius algebra, and it's a Hopf algebra object in there.
Yes, exactly. So basically, yes, you don't go to K, you go to modulus of Frobenius algebra. Yeah.
Yes, exactly. So I'm not sure how much you can do with abstract Hopf algebra objects in some weird category, and this might cover some weak Hopf algebras. But if it's not symmetric, the braiding, then things certainly break at some point. You have to be much more careful than we were.
Sure.
But there might be a route to do this very elegantly in one go.
So, Sebastian, are you saying any weak Hopf algebra can be thought of as a Hopf algebra object in some category? I don't think that's a...
I'm not sure whether I want to. I think I want to assume semi-simplicity here.
Yes.
Even for semi-simplicity, I mean, are you claiming in terms of their representation, the category, like?
Okay. Actually, I have a paper in mind. If I find this, I will search it in the background. I'll post a link to the chat and yes, exactly that paper. Perfect. Thank you very much. So
okay.
and I'll send an archive link, or
okay.
maybe Colleen will be actually quicker than I am. Let's see. And yeah, we can discuss this later. Sorry for interrupting. So yes, if there aren't any additional questions, I would say Uli can continue with the research part of the talk, and I'll post the paper in the background.
Good. Okay, so right, I hope we all have some vague understanding of what a Yetta-Drinfeld module is. And so what Sebastian and I found is that we need to look for this non-semi situation at a generalization of Yetta-Drinfeld modules, which are twisted by Hopf algebra automorphisms. So we did not invent them, they were there already, but they kind of pop up whether you like it or not. And that's what kind of was maybe one of the interesting insights of the paper, I would say. But let me go a step back and kind of tell you how we arrived at this, and why I really find that Kitaev model so beautiful, also from the point of view of pure abstract algebra and geometry, right? Even if I'm not interested in any applications of quantum computation, if you stare for long enough at this Kitaev construction, it looks very, very beautiful and natural, I would say. And kind of all the ingredients that feature in it kind of make sense in this picture, I would say. So in particular, I haven't said that. I said I choose a graph, but also for the models that we kind of generalized, you also need to choose a direction on the edges of this graph. So the edges of the graph carry small arrows, which at the end of the day don't matter, but they have to be there in the first place. And if you now zoom in on one such edge and you are on a two-dimensional manifold and it is oriented and the graph is directed, then you can always think of a picture like this locally around each edge. And then you realize, okay, each edge then has a starting vertex, a source vertex, and it has a target vertex, an end vertex. And it also has a left face and a right face, okay? And And I think what one really wants to see is a generalization of the Kitaev model where you decorate this with some categorical structure. And in particular, when you look at the formulas of the Kitaev model in this Hopf algebraic setting, you see that, okay, people always write a Hopf algebra onto this edge E, but they do not really use the fact that this is a Hopf algebra. They use the fact that it's a bimodule and a bi-comodule. And I think more generally, there should be a picture in which the vertices of these graphs get decorated with algebras, the faces of these graphs get decorated with co-algebras, and the edges get decorated by bimodules over the two algebras at the end and at the beginning of the edge, and by bi-comodules over the two co-algebras which sit to the left and to the right of the edge. And then there's something really beautiful about two-dimensional mathematics and Poincare duality on surfaces, which says that, look, co-algebras are dual to algebras. And then there's stuff like graph duality, where you would say, there's the dual graph on the same surface, where you think of these faces suddenly as vertices, and then these vertices become faces. And kind of this should, at the end of the day, really be the mechanism behind the Kitaev model. But we haven't gone so far in the first paper yet. So we have one Hopf algebra curly A, which let's assume it's finite dimensional over a field. But already we kind of toy with the edge decoration, and we do no longer assume that we just write the Hopf algebra on the edges, but we write a bimodule, bi-comodule M onto these edges. And we started from there, and then we tried to work out what are the exact assumptions that we need to make to have these theorems work at the end, okay? And what we found is that there's a compatibility between the actions on these bimodules and the co-actions on these bimodules that is in this definition here. So you need some additional input datum here, some automorphism of the Hopf algebra or bi-algebra A. And then you can define these sigma twisted Hopf bimodules. So they are bimodules and bi-comodules over A. So there are vector spaces M, which come with a left action and a right action, which turn this thing into a bimodule. So I can multiply elements small m, think states, from the left and from the right by elements A and B in the algebra. But they're also bi-comodules. So there's also a left and a right coaction. So if I want, I can make M spit out elements in A to the left and to the right. And I write this in this Sweedler type notation. So in this, the M0 part always stays within M. The minus guys are coming from the left coaction. The plus guys come from the right coaction. And now the compatibility condition is this. You could first act with A and B on M, and then you do the two-sided coaction. This is this side. And I want this to be the same as this. I first coact, so I get M-1, M0, M2, M1. And then I act from the left with what I get by applying the coproduct in A twice to small a. So I get A1, A2, A3. And I act from the right with B1, B2, B3. But no, at the end, I apply that sigma. So for sigma equals the identity, this is what's called Hopf bimodules, and which is described in any Hopf algebra textbook. But you can look at this slight generalization and you get some category. Okay, and we will find that precisely this matters for the Kitaev model. Now, if you look up in Hopf algebra textbooks what can be said about these Hopf bimodules, then you will quickly find the theorem that the category of Hopf bimodules, sigma being the identity, is equivalent to the category of Jeter-Greenfeld modules. So these Hopf bimodules are simply a different way to describe Jeter-Greenfeld modules. And this correspondence between Hopf bimodules and Jeter-Greenfeld modules also extends to such a twisted setting. And how does it work? If you start with such a sigma twisted Hopf bimodule M, you can assign to this the left invariance under the coaction. So you take just those elements M, those states, where the left coaction doesn't spit out anything but the unit element of the Hopf algebra A. In an abstract way, one can say this is the cotensor product of the left comodule M with the trivial right comodule C, which spits out a 1. Okay, so this is then a subspace of M. Because the left coaction commutes with the right coaction, it's a bicomodule. This subspace will be a sub-right comodule. So this carries a right coaction of A. And you can also then write down this right adjoint action, which combines the right action and the left action and the antipode in such a formula here. And you will then compute that in this way, you get some sort of Jeter-Greenfeld module. Yeah, it's a right module, it's a right comodule, but the compatibility condition is a bit different. Somewhere at some point, this sigma features. And I said Jeter-Greenfeld modules without twist correspond to such braidings. And now here we get this generalized braiding. Yeah, so C is such a twisted Jeter-Greenfeld module. Now take any other right A module H, then you will get a map from H tensor C to C tensor H twisted by sigma. And the map is precisely this Jeter-Greenfeld braiding that we had seen before. But it's now no longer, if the twist comes in, an isomorphism from H tensor C to C tensor H. It's an isomorphism from H tensor C to C tensor H sigma. And by H sigma, I mean you take the same vector space as H, which is a right A module, but the new right action first applies this automorphism and then acts. So sigma twisted Jeter-Greenfeld modules give you these strange braidings which do this for you. And they correspond to such sigma twisted Hopf bimodules if you're talking about a Hopf algebra. Okay. Now, there's one case which is particular, which is when you take sigma to be the square of the antipode. And then you can think of the role of these Jeter-Greenfeld modules in a different way. Now, in this case, these twisted Jeter-Greenfeld modules were called anti-Jeter-Greenfeld modules by a bunch of people, Hayat, Kakali, Rangipur, and Sommerhäuser. So they looked at something which has nothing to do at first sight with what we are talking about here, namely Hopf-cyclic homology. I will maybe say a few words about that at the end. And they found that such anti-Jeter-Greenfeld modules feature as coefficients in Hopf-cyclic homology. Okay, but it's precisely the definition of an anti-Jeter-Greenfeld module is exactly such a sigma twisted Jeter-Greenfeld module, where the twist sigma is the square of the antipode. Now, I said the antipode is always an algebra antimorphism. If you square the antipode, you get an algebra automorphism. And you also get a co-algebra automorphism, in fact. So yes, the square of the antipode is always a Hopf algebra automorphism of the Hopf algebra. And if you give me such an anti-Jeter-Greenfeld module, then I can get a tracial functor on the category of left modules over A. So the category of left modules over my Hopf algebra is also a monoidal category. And I can take a left module and I can tensor over A with that right module C, with that Jeter-Greenfeld module, that twisted Jeter-Greenfeld module, well, the anti-Jeter-Greenfeld module. And I can now see that there is an identification between this and that given by such a map, which again looks a little bit like these Jeter-Greenfeld maps or these canonical maps. I have to put an s to the -2 in here, so I have to assume here that s is bijective. Okay, so I said if I take a standard Jeter-Greenfeld module, no twist, sigma the identity, then this is the center of the monoidal category of right modules. Yeah, meaning it's the Greenfeld center. In more abstract terms, it's the zeroth Hochschild cohomology of that monoidal category. The anti-Jeter-Greenfeld modules, they are the zeroth Hochschild homology of that monoidal category. They are the co-center, so it's functors from that category to abelian groups, which are traces. So they don't see the difference between H tensor K and K tensor H. And in general, the category of Jeter-Greenfeld modules and anti-Jeter-Greenfeld modules they differ. You know, for a general Hopf algebra, you might not have any identification with these, as you can read in Sebastian's PhD thesis, for example. Yeah, but there's, as you see, a very, very natural way how these anti-Jeter-Greenfeld modules also appear. So Jeter-Greenfeld modules, anti-Jeter-Greenfeld modules are simply the center and the cocenter of these two monoidal categories that you associate to your Hopf algebra, the left modules and the right modules. Okay, and now, how does this come in touch with the Kitaev model? I said that to write down the Kitaev model, we have to choose directions on the edges of our graphs. But the key point is that at the end of the day, that protected space that you write down should not depend on the choice of directions that you've made. And we toyed with these twisted Hopf bimodules to kind of get an edge decoration where we kind of can identify something in one way and in another way. And this one way and another way comes with this involution, kind of the incarnation of that idea is this involution here. Okay, so if we have a Hopf bimodule, we can use the antipode or the inverse of the antipode to kind of turn the left action into a right action and the left coaction into right coaction and vice versa. And you can then ask yourself whether this flipped action and coaction could lead to a Hopf bimodule which is isomorphic to the original one. And what you find is that for this, the twist must come in and it must be an s to the -2 twisted Hopf bimodule. And with that twist, so if you have an s to the -2 twisted Hopf bimodule, you can then ask for a linear involution. Small m is mapped to m circ on that vector space M. So a linear map which squares to the identity, which intertwines these two things. So it kind of has these properties as you see here. And I claim that it's this kind of algebraic structure which on the nose kind of serves what you need in the Kitaev model to write down that protected space. And when you kind of approach this whole thing from a more Hopf algebraic perspective, you will at some point write down precisely these formulas and only these. Yeah, you cannot do an s to the -7 here or whatever. Yeah, these are kind of the formulas which nature throws at you. Well, and if you have this, how does the Kitaev model work? So you give me such an s to the -2 twisted Hopf bimodule M. Okay, and then the claim is that as in the standard setting that everyone discusses, you get a Jeter-Greenfeld module over the S-fold tensor product of your Hopf algebra A that you have chosen. So the extended Hilbert space is now an L-fold tensor copy of this twisted Hopf bimodule. So this is kind of my qubit or qudit that I put on each edge. And the formulas for these Jeter-Greenfeld module structures, so they have been in the literature. So for example, there's a paper by Shawn on this matter. To be honest, this is what I find so hard in this whole Kitaev business. There are so many papers that it's completely impossible to really get an overview of the literature. I mean, in what I usually do, there's maybe 10 or 20 people who are interested in the questions. So if you have a new idea, you ask all of them and they say, oh, great idea. Yeah, we'll see what comes out. And then you write your paper. Whereas here, it's very unclear whether what you do is already known somewhere. But the formulas go like this. Yeah, so let's do this in the very simplest example to give you a feeling. Suppose we go back to the toric code and we actually choose a 1 × 1 lattice on the torus. In other words, we just write down 1 vertex and 1 face and 2 edges. Okay, so you now see here the torus. Now it seems there are 9 vertices. Of course, these are all the same vertex, which is drawn here. Now there's 1 edge which kind of goes down here and then winds around the 1 torus circle and comes out here. And there's the other edge which goes up and comes out here. Now, if you have a state small u tensor V in my extended Hilbert space, which is now a tensor copy of 2 copies of M, What's the Jeter-Greenfeld module structure? Well, there should be an action of A and a co-action of A, and I write down the action of A. And what you do is, so for each site, well, there is only one site now, which is this one here. It works like this. You give me an element small a in my Hopf algebra, and then I go counterclockwise around the vertex. And whenever I cross an edge, I kind of act with something either from the left or from the right, and maybe some antipodes get applied. So I see that on my full circle, I seem to cross 4 edges. Well, in reality, I cross that edge here twice and that edge here twice. But if I'm a local particle, I will never know this. Yeah, just locally, it seems I've crossed 4 edges on my path. So the first thing I do is I apply the coproduct 3 times to small a. So this produces an element in A tensor A tensor A tensor A, which in this Wheeler notation has A1 tensor A2 tensor A3 tensor A4. And now I keep moving on my path. I hit the first edge. This is decorated with the state U. Okay, so, and the direction of the edge, I've chosen this one. So here my edge comes from the right. And when my edge comes from the right, so my A will act here from the left. And it's the first component of this triple coproduct of A that I apply. So the A1 acts from the left on this U, then I keep going, I will meet a second edge. This time the edge comes in from the left. So I now will act with S of A2 from the right on whatever is here. I keep going, then I again hit the same edge, but this time it comes in from the left. So S of A3 acts here. I keep going, and I again hit the second edge, but this time it comes in from the right, so A4 comes here from the left. So if you've seen this for the first time, this was a bit fast, but there is a recipe here where you start in a site, you choose a vertex, you walk around that vertex counterclockwise, and then there's a formula which produces an operation of the Hopf algebra A onto kind of all these vertices, all these edges which are attached to the vertex. And there's a similar formula which gives you a coaction. And then you do a big computation and you find that if what was on the edges is such an s to the -2 twisted Hopf bimodule, then indeed at the very end you get a Jeter-Greenfeld module over A tensor A tensor A tensor A tensor A. And more than that, if you have isomorphic graphs drawn onto your surface, these Jeter-Greenfeld modules that you get will be isomorphic as Jeter-Greenfeld modules. And now one has to be a bit more precise what one means by isomorphic graphs. And one way to say this would be by saying, okay, when I draw these graphs onto my surface, I can thicken these graphs a little bit, and then I actually get small two-dimensional submanifolds with boundary called ribbon graphs, which are drawn onto this surface. And the statement is that, well, I cannot take arbitrary ribbon graphs. They have to kind of satisfy these assumptions that they give these bijections between vertices and faces, and then you have to choose all these directions. But at the end of the day, with these assumptions, if the ribbon graphs are diffeomorphic as manifolds, the Jeter-Greenfeld modules that you associate to your situations will be isomorphic as Jeter-Greenfeld modules. And that's the first part of the game. Okay? So from certain algebraic input data and any Hopf algebra, semi-simple or not, if you give me such an s to the -2 twisted Hopf bimodule, we can write down a Jeter-Greenfeld module. And the Jeter-Greenfeld module only depends on the graph up to isomorphism. Now the second step, and the harder step, is to kind of get the analog of Kitaev's theorem that the dimension of the protected space does not depend on the graph chosen at all. It only depends on the genus of the surface. We'll get to that in a minute, but before getting there, I want to already mention something which will feature there, namely Redford's S to the 4 formula. I told you that when you come to this anti-Ether-Greenfeld module business, from the point of view of Hopf algebras, it's the twist given by S squared, which is the most interesting. These are the anti-Ether-Greenfeld modules. And then I said, when we did the computations for the Kitaev module, it's the inverse of the antipode squared, which is the twist that we use. So this seems to diverge somehow, but there is a theorem that if you have a finite dimensional Hopf algebra, then the fourth power of the antipode can only always be realized with such a conjugation-like formula. So there's a group-like element small p in the Hopf algebra. So an element p such that its coproduct is just p tensor p, and epsilon of p is 1. And it then follows that this is an invertible element. And there's a group-like element in the dual Hopf algebra, which means simply a character on the original Hopf algebra, a one-dimensional representation, such that the fourth power of the antipode is conjugation by this element p and by that character, by which we mean this formula here. And from this it follows that actually the category of S squared twisted Hopf bimodules, or equivalently Ether-Greenfeld modules, is equivalent to the category of S to the -2 twisted Hopf bimodules. Yeah? So for a finite dimensional Hopf algebra, when you play this business with the twisted Hopf bimodules, you need Hopf algebra automorphisms, and you immediately say, well, we could use all the even powers of the antipode as such Hopf algebra automorphisms and see what happens. But then Radford's S to the 4 formula tells you there are actually only two cases to consider, the identity or S squared, because S to the 4 will be again equivalent to the identity, so will be S to the 8, S to the 12, etc. Whereas S to the 2, S to the 6, S to the 10, they will all be equivalent in themselves. So at the end of the day, for finite dimensional Hopf algebras, there's just two types of canonical twisted Ether-Greenfeld modules to consider, the Ether-Greenfeld modules and the anti-Ether-Greenfeld modules. And kind of one of the main messages of today is that if you want to do the Kitaev module, somehow it's the anti-Ether-Greenfeld modules that you should use to kind of build your Kitaev models. Good. Now, why did no one notice this so far, right? All these other people who worked with Kitaev models for Hopf algebras did not need these anti-Ether-Greenfeld modules. And this theorem here is the answer to this. Well, there's a famous theorem which says for a finite dimensional Hopf algebra, semi-simplicity precisely means that S squared is the identity. So when you work with semi-simple Hopf algebras, this business about the twist disappears entirely. And that's why when you work with semi-simple Hopf algebras, you do not notice this twisted stuff in the Kitaev model. Yeah? But somehow this is a very strange theorem, I would say. A priori, semi-simplicity, why this has to do with S squared being the identity, is completely opaque at first. And when you then stare at the Kitaev model and the proofs, you really see, no, the crucial thing is not semi-simplicity, it's that S squared is the identity. That's what people really use. And then in some lemmas, they use semi-simplicity and projectors and all that, but this is what we wanted to circumvent and manage to do. Good. And well, so as I said, we will now kind of get into this definition of these protected spaces, where we kind of generalize this formula where S squared is the identity, and we use kind of inspiration from two sources which are in a sense equivalent. One is this Hopf-cyclic homology business of Kohn and Moscovich, and the other one is when you think about what is a pivotal structure on the category of Ether-Greenfeld modules. Good. So, final part, protected spaces via bitensor products. Now, so Kohn and Moscovich, as I said, they were coming from a completely different angle. So they were looking at non-Knuth geometry and index theory in the setting of Kohn's non-Knuth differential geometry, and they associated certain universal Hopf algebras to foliations. You know, if you have a foliation of a certain codimension, there's a universal Hopf algebra that kind of then acts on algebras of functions on the foliated space. and they wanted to have kind of index theorems for elliptic differential operators, which are transverse to the foliation. And they used Hopf-algebraic techniques and the new cohomology theory of Hopf algebras that they found, this Hopf-cyclic homology. And for this, they needed coefficients, and these coefficients are these pairs in involution, as they call them. And a pair in involution is basically almost the same thing as we have just seen in Radford's S to the 4 formula. But we don't do this with S to the 4, we do it with S to the 2. So a pair in involution for a Hopf algebra is a group-like element and a character on the Hopf algebra, such that when you conjugate by the character and the group element, you get S squared. And a pair in involution is called modular if the character evaluated on the group-like element is equal to 1. Okay, so Kohn and Moskowitz were interested in these modular pairs in involution because when you give me such a thing, they could write down invariants of the Hopf algebra called Hopf-cyclic homology. And then afterwards, people came and tried to generalize this, and they then came up with these anti-Edler-Greenfeld modules and said, well, if you take anti-Edler-Greenfeld modules and you take them to be one-dimensional as a vector space, well, a one-dimensional module is precisely a character on an algebra. A one-dimensional co-module is precisely a group-like element of the co-algebra. And then this strange condition down here of Kohn and Moskowitz precisely becomes the anti-Edler-Greenfeld condition that we have seen before. Okay, so you should think of these modular pairs in involution as one-dimensional anti-Edler-Greenfeld modules. Okay, and if you want to know more about Hopf-cyclic homology, I can easily talk forever about this, but I would say not today, or at least not unless you ask me. So they will feature, and then a strange bifunctor will feature, which I should say, I mean, the last talk was by Catherine Meusburger, and while we were working on this project, we talked a lot to her to understand her work, and kind of she pushed us into this direction, I would say, to use this type of structure. So in her papers, she talks about the bi-invariants, and when you stare at these for long enough, you realize that it's this type of bifunctor which generalizes these bi-invariants. And I admit at first, this thing looked horrible to me. So what's going on here is, give me a Hopf algebra A, or a bi-algebra is enough. Give me a right module and right co-module R. Give me a left module and left co-module L. Then I can do the tensor product of R with L just as vector spaces. I can, of course, also take the tensor product of R and L as modules. So I can tensor over A. And this is a quotient of the vector space tensor product of R with L. I could also consider the co-modules and do the co-tensor product of these two. This is a subset of the vector space. Now, it's the subset, completely dual to the tensor product of modules, the subset of those tensors, which give you the same thing if you now coact either on the first or on the second tensor component. So the co-tensor product embeds into this vector space tensor product. The tensor product of modules is a quotient thereof, and the bi-tensor product is obtained by looking at this combined map and take the image of this in here. And this generalizes the bi-invariants that Catherine uses. And well, once you stare at this, you realize, okay, this is a bifunctor, nice. It's a little bit like tensor products or co-tensor products, but it is neither left nor right exact. Yeah, it's an additive bifunctor, which is neither left nor right exact. Hence, from the point of view of someone who usually does homological algebra, this is a pretty bad thing. In particular, how to do homological algebra with this is a bit nasty. But it is an additive bifunctor. And of course, it has been considered by other people. So I think the earliest reference who seriously looked into these was by Hofstetter in 1994. Okay, so you can do this. And well, the final theorem is this. So suppose you have such a Kitaev model, which comes from a Hopf-algebra A. So Shawn asked, what are the conditions? The conditions are, you have a Hopf-algebra A, and the Hopf-algebra A must have a pair in involution. And again, so the first paper of Sebastian's life was to show that there are finite dimensional Hopf-algebras which do not have such pairs in involution. So there are finite dimensional Hopf-algebras which don't have pairs in involution. So this is an assumption, and it's also a choice. Yeah, you choose a pair in involution. Some have more than one. As I said, this pair in involution will be a one-dimensional anti-Jeter-Greenfeld module. I also said that there is a canonical correspondence between twisted Jeter-Greenfeld modules and twisted Hopf-bimodules. So you can use this one-dimensional anti-Jeter-Greenfeld module, produce a twisted Hopf-bimodule M from it, which will look like this. So this is now a potential edge decoration for our Kitaev model. Okay, so you can then do this Kitaev model thing. You get the extended Hilbert space H. It is a Jeter-Greenfeld module over this S-fold tensor product of a Hopf-algebra with itself. And now we wanted to write down protected spaces. And we write down these protected spaces using this bitensor product with some right module, right co-module. And this is what took us the longest time. We tried to find for which right modules and right co-modules we're able to write down a protected space, and we're able to prove rigorously that its dimension will not depend on the chosen graph gamma. It only depends on the surface sigma that we have chosen. And the answer that we found looks really strange. I totally admit that. I still feel, I'm pretty sure what we did is correct. Whether there's a more beautiful and statement with an easier proof, I don't know yet. This is as good as we got it. So you can take a certain right module, right co-module, which is obtained by kind of putting on every vertex of our graph such a right module, right co-module. This is really strange. You take that pair in involution, you manufacture from it something which you might at first think is just the square of that anti-Jeter-Greenfeld module, but it's not. There's an inversion going on up here. So you take this one-dimensional right module, right co-module, attach it to every vertex but one. So there's a distinguished vertex that you pick. And at that distinguished vertex, you can put anything you like. And the choice of that anything you like is like the choice of the energy level of your quantum computer. So the protected space in the original model is the degenerate ground space of your quantum computer, but you could also choose excited states, and they would be also topologically protected. And the choice of the eigenvalue of your Hamiltonian gets generalized to the choice of that right module, right co-module, which you place at your distinguished vertex. At all the others, you put that strange one-dimensional guy, which I have no explanation for. You then manufacture this X, which is a big tensor product of all these. You take the bitensor product, call this the protected space. Theorem, the dimension of this does not depend on the chosen graph. It only depends on sigma. End of talk. Thank you.
Okay, perfect.
Thank you.
Are there any questions?
So this involution pair, do they always exist?
No.
Okay.
So this was an old story. So they were floating around, and Piotr Hoyerts had asked me a long time, are there Hopf-algebras without a modular pair in involution? I said, yeah, sure. He said, write one out, write one down. And after he asked me 3 times, I sat down, I wrote down an example of an infinite dimensional Hopf-algebra, which does not have such a pair in involution. And then he got back to me and said, oh, but I want to find a dimensional one. I said, yeah, you can also find one of these. And then I tried and I failed. So I kept thinking about this now and then. And when Sebastian started his PhD, I thought, okay, here's maybe a good question. I had a rough strategy how to find a counterexample. I asked Istvan Heckenberger, who is kind of the top expert in the area of Nichols algebras, which I wanted to use to construct the counterexample. And Istvan usually replies after 10 minutes with an answer. And this time it took him a week or so, and he said, oh, I have absolutely no idea. So maybe it's indeed a good project for your student. And I thought, well, if Istvan needs to think for a week and has absolutely no idea, maybe it's not a good project for a student. But we tried anyway, and then Sebastian came up with a solution within a few months, and that was the first paper we wrote. So yes, there are finite dimensional Hopf algebras with no modular pair in evolution. There are also finite dimensional Hopf algebras which have several pairs in evolution. What exactly that means, I don't know.
So here you don't require, like in this evolution pair, you don't require, for example, p square is the distinguished group-like element in the Radford formula.
Indeed, yes, yes. It's like choosing a square root of the distinguished group-like. Yes.
Yeah, I mean, in the case if you require p to be a square root, and also similarly for chi, then in the literature, I think this condition is on the Hopf algebra. It's called a doubly balanced condition. This is equivalent to the Drinfeld double of the Hopf algebra being a ribbon, yes, category, I think.
Yes, it's the pivotality. So these, yes, I mean, Kaufman had kind of also introduced these.
I was referring to his result.
Yes, that's true. It's true. It's precisely the choice of a pivotal structure on the Eta-Greenfeld modulus, i.e. on the modulus over the Greenfeld double. You can read it like this. Yes.
Okay, got you. Thank you.
One should add, if you start with any Hopf algebra, anyone you like, then the only thing we really require is the antipode is invertible. If you find these pairs, great, you can start the machinery immediately. If you don't find these, you can add a single group like, and then it will have a pair in involution. So every Hopf algebra embeds into one which has a pair in involution. So
that's true. This
is really, once you have an invertible antipode, you can build all of this and get the machine going.
But I thought a finite dimensional Hopf algebra always has an invertible antipode.
Yes.
But we don't need finite dimensional. This is any Hopf algebra.
I mean, even for the Kitaev model, you don't need finite dimension condition.
No, this was, I mean, we had kind of initially written down everything for finite dimensional because we felt it would be easier, but at the end of the day, it's actually not relevant. So finite dimensional doesn't matter.
Okay.
One could add, in the semisimple case, a semisimple Hopf algebra is automatically finite dimensional. So this is another reason where if you assume semisimplicity, you only have finite dimensional Hopf algebra. So this can also only really happen in the non-semisimple case.
Okay.
Yeah, so I think the upshot is semi-simplicity really is not needed. This is kind of a red herring, I would say. It's really about this S squared thing, which is about, in purely categorical terms, it's about the double dual of an object. Yeah, you take the dual and again the dual. And basically what this says is the double dual is isomorphic to the original, right? You simply act with chi and with p, and that gives you the isomorphism between the left and the right dual, or between the object and the double dual.
I thought this involution is weaker than a pivotal structure. Okay. Okay. You guys, I guess you mean the double dual in the Drinfield double, right? Not
Yeah.
in the. Okay. Yeah.
Yes.
Yeah, okay.
Yes.
I see.
So
And
yeah,
do you expect these construction to also apply to Hopf algebra objects in like a braided tensor category?
yeah, I think at the end, yes, I would say at the end of the day, it should not be about Hopf algebra. It should be about monoidal categories. Now, start with a nice rigid monoidal category or just pivotal monoidal category or something like this, and then you should be able to run that business, I would say.
Yeah,
Yeah,
I mean, this is essentially the non-semisimple 11-1 construction, I think, eventually.
Yeah, I mean, it doesn't even have to be in Hopf. I think definitely it will work for Hopf algebraics, but maybe even for Hopf monads, I would say. Because really, at the end of the day, the Hopf algebra is just there to produce this category of twisted Hopf bimodules. And the category of these twisted Hopf bimodules is simply some cocenter of some monoidal category. And I think the ultimate picture I want to see at some point in one future paper is that, yeah, you can start with some monoidal category. Maybe you have to choose a module category over this, and then under assumptions A, B, C, you can decorate the edges of graphs with objects from that category. And then you get a kind of TQFT-like interpretation of that story.
I mean, I mean, what you're saying, that's essentially called 11-1 model in the semisimple case. So, I mean,
Come again?
That's called the 11-1 model. 11-1.
Okay.
Yeah, I mean, basically, in the semisimple case, this Kitaev model and 11-1 model, they're related exactly by passing a Hopf algebra to its representations.
Mm-hmm.
And I mean, these two models as a TQFT, they define their equivalent. So I suspect, if you pass to non-semisimple monoidal categories, what you build is a non-semisimple generalization of the 11-1 model.
Yes, I guess, yeah, no, that's true. I mean, we were also looking into papers on this, but yeah, we didn't yet see how exactly things translate. But I totally agree. This is definitely something to be pursued. Yes.
Great. Yeah, thank you very much for giving such a nice talk.
My pleasure. Thank you for the invitation. Okay.
So I would turn off the recording unless anyone wants another question recorded, but I don't think so.